right, here we are. We have made it to our last lecture of the year. And this should be a pretty short one because all we have to do really is introduce the lab technique that we are going to use in our virtual lab starting on Friday. So it should be pretty quick and painless. All right, so this lab technique that we're going to talk about is called a titration. This is just so widely used in chemistry that it would be a huge disservice if we got through an entire year of chemistry and didn't mention titration. So it'll be the last thing we do. In general, the definition of a titration is just a lab technique that is used to determine the unknown molarity of a solution. Okay, so we have a solution, we don't know the concentration of that solution, so we use this technique to figure that out. And the setup is pretty simple. So I've done a terrible drawing over here of the setup, but basically we have a couple pieces of glassware that we use. The first is, it's called a burette. And if you think back, when we use different types of glassware in lab, the pieces of glassware we used if we wanted to measure out volumes very precisely. Do you remember what we used in lab? It was the graduated cylinder, right? We didn't use a beaker because it wasn't as precise. Well, this burette is even more precise than the graduated cylinder, so it's able to give us volumes very, very precisely down to the hundredths of a milliliter. So we have a burette, and the burette will be filled with one solution that we will call the titrant. Okay, Titrant. The titrant goes inside the burette. And then we have another flask here below the burette. And inside that flask, we'll put another solution called the analyte. Okay. And the way you do titrations is you have to know the concentration or the molarity of one of these solutions, right? You have to know one, the other is the unknown that you're trying to figure out, okay? Now, a lot of people say the known molarity solution has to go in the burette or has to go in the flask. It doesn't really matter. You can put the known or unknown molarity solution in either the burette or the flask. It really doesn't matter. But in the analyte, we will also put another very important component. We will also put what's called an indicator. Okay, and this indicator is going to give us a qualitative method to know when the titration is over, when you know that the titration is done, okay? And when it's done, that's what we call the end point of the titration. It is a qualitative end to the titration. And we say it's qualitative because these indicators are usually solutions. They're little solutions that we add in little amounts that change color when the titration is over, okay? So our general setup is pretty simple. We have our burette with the titrant inside the burette. In the flask below, we have the analyte with an indicator, and then we will start mixing them until that indicator tells us that we've reached the end point, okay? And now, there are lots and lots of different types of titrations that chemists perform very regularly, but of course, we are going to be talking about a specific type, an acid-base titration. We're even going to do a more specific type of acid-base titration where we only use a strong acid and a strong base. Okay, so think back, we kind of just listed out all of the strong acids and strong bases that you need to know. So we're not going to be using any weak acids or any weak bases. You could, it's just a little more difficult and we just don't have enough time to do that. So strong only, okay? So I'm going to put the acid inside the flask, and that will be our analyte, which means that our base will go here in the burette, and that will be our titrant, okay? And so we are going to also add an indicator. It's called phenolphthalein. It's a big, long, ugly word. That is going to be our indicator that will change colors when we finish or when we reach the end point of our titration, okay? And so I want to show you what that means to get to the end point of an acid-base titration. And to do this, I'm just going to do it with a graph because I think that's easiest to see. And what we're actually monitoring in an acid-base titration is the pH of this analyte, okay, in the flask. So I'm going to plot the pH, and that'll be the pH of what is in this flask. And then on the x-axis, I am going to put the volume of base added. Okay? Because all we're basically doing is we have this acid in here, and then we are going to slowly drop in the base into this flask until we reach that endpoint. Okay? And this is what we mean. So think about it. If we're plotting the pH of this analyte in the flask, it's the acid. So the pH is going to start, good, low. So I'm just going to arbitrarily choose a low pH. It doesn't really matter what the value is. But as we add volume of base, if we have a strong acid and a strong base, what's going to happen is the pH is really not going to change much at the beginning. Okay? You're going to start adding base. It's not really going to change the pH all that much. It'll start to increase just a little bit because we're adding base, but it actually stays relatively constant. And then all of a sudden, it's going to shoot up and then level off. Okay? And this is what's called a titration curve. Now, what this shooting up represents, okay, it's the volume of base that is required to get to a pH of 7. It's to neutralize that acid, okay? So we are adding base, base to this acid until we reach this neutralization point where we have the concentration of H plus ions from the acid now equal to the hydroxide concentration from the base. Now, we already know when those two things are equal in solution, they're going to be 10 to the minus 7 molar, and that would give us a pH of 7, okay? This is where we want to end the titration. This is when we know that the hydrogen ions and the hydroxide ions are equal. That is our equivalence point, and that will hopefully be our end point of the titration. Luckily, this phenolphthalein, we use this strategically because it changes colors very, very quickly right when you get around this equivalence point, okay? The end point of your titration. It's clear when it's at pH values less than 7. So if it's in an acidic solution, this phenolphthalein will be clear. But then right when you get above pH 7, it's actually like a little like pH 8, but pretty close to this equivalence point. Right when you get above that pH, then this indicator turns pink. Okay? Right when it turns pink, that's our qualitative way to know that the end point has been reached and our titration is over. So this is what we're going to do in lab. We are going to figure out how much of the titrant you need to drop into the flask in order to reach this end point of our titration. And we'll know this just by qualitatively watching the indicator turn from clear to pink. Okay. This chemistry lecture brought to you by, I don't know. I'm out of ideas. It's the last lecture. So here's my puppy. Okay, so the last thing that we have to do is I want to show you how we do the calculations for titrations, because remember, our goal for a titration is to figure out the unknown molarity of one of your solutions. So I just want to show you how we go about that. So for this titration, our theoretical titration, the acid I'm going to use is HCl, and then the titrant here is going to be our base, and I'm going to use sodium hydroxide. Okay, so let's just say we have 35.0 milliliters of HCl, and we know that it has a molarity of 0.855 molar. Okay, and then we're going to fill up this burette with sodium hydroxide. So let's write the chemical reaction that is going on in this titration. So we have hydrochloric acid and sodium hydroxide. Being that it's going to be a strong acid and a strong base always for us, this reaction will always produce the same two products. Okay, it's always going to give us what we call a salt, an ionic compound, and water. Okay, but it's just a double displacement reaction. So if you remember back to our chemical reaction types, these two are just going to go through a double displacement reaction or double replacement, whatever you guys call it, and we will end up with sodium chloride and water. Okay, so here's our salt, literally, it's just table salt in this case, and water. So we need to balance it, but this is a 1-to-1 ratio. It's already balanced, so it's a pretty easy one. All right, now we're gonna do this titration, wait till that indicator turns pink. Right when it turns pink, you're done. And it turns out that it took, let's say, 16.25 milliliters of NaOH in order to reach that endpoint, except we just don't know the molarity of this base. Okay, so at this point, if you can reach back into your memory of stoichiometry, all this is, in order to figure out the molarity of this base, all it is a simple stoichiometry problem where you're starting all the way up at the top of our mole road with volume, and then we're just going to go straight down the mole road to the other volume. Okay, so if you can picture that in your head, you'll go from volume to moles, then you'll use the mole ratio, and then you'll go back to volume. And in order to do that volume to moles conversion, we're just going to use the molarity equation. So in order to do this, we're going to start with our known amounts for the acid, and we're going to use our molarity equation, which is just moles over liters. Okay, and so in order to do that, we have 0.855 molar equals X moles over 0.0350, because we have to use liters, we cannot use milliliters. If you do that, you'll get your moles of HCl, right? This will be moles of HCl. It turns out that it'll be, if you want to do this calculation, quick, go for it, but it's about 0.03 moles of HCl. Then we can start our little stoichiometry calculation because we have moles. Now we just need to use the mole ratio. Luckily for us, this is just a 1-to-1 mole ratio, so it's not going to change. But just be careful, it's obviously not always going to be a 1-to-1 ratio. And then that will give us, of course, same number of moles, 0.03 moles of NaOH. Now we're just going to use the molarity equation again. We have 0.03 moles all over the volume that we use, 0.01625 liters. And if you plug that into your calculator, you should get a new molarity of 1.84 molar. Okay, so we use this titration with one solution that we did not know the molarity of, one solution that we did know the molarity of. We did the titration until its end point when the pH is equal to 7. meaning the H plus ions are equal to the OH minus ions. Because of that, we're able to set them equal to each other. We use the mole-to-mole ratio in order to get the moles of our unknown solution, and then just plug that into your molarity equation at the end. So this is going to be the general setup for every titration problem that we do. Okay, so in your lab, you're going to have 6 titrations where you're actually going to set this up, and then you're going to drop in the solution into the flask in very precise amounts until it just turns pink, and then you'll do your calculation based on how much you dropped in, and then you'll figure out the unknown molarity. Okay? All right, guys, that's it for this year. That's all of our lectures. I know this wasn't ideal, but I appreciate you guys hanging in there and still learning chemistry remotely on your own. I know that's hard when you can't actually ask questions during the lecture. But I hope you guys got something out of these lectures, and you're all going to do so well in AP Chemistry next year. All of you, right?